Hello and welcome to Fluid Mechanics. This video is going to concentrate on a specific example of a planar surface exposed to a fluid and the pressures of that fluid. Previously, we talked about some of the fundamental concepts of this, so we're going to do a specific example, and hopefully you can appreciate once we do this problem, it's really a similar process for any other planar surface exposed to a fluid. So let's jump into it here. On the left-hand side, we have a fluid retaining system for water, and it's composed of this pink gate here, and this gate is held in place by a hinge here at point A and contact with a retaining wall here at point B that holds it from rotating. The gate is 10 kilonewtons in weight. Its dimensions are 2 by 2 meters, and we want to focus on finding that force at B that holds it in place. This might be important for verifying that this wall is strong enough. Okay, so one of the big ideas we need to focus on for this is pressure and how it kind of works. If we can get that down, we're going to use a lot of concepts we've done in other courses like physics and statics in the past. So pressure has three main ideas we need to focus on here. So the first idea is pressure at a point in a fluid acts equally in all directions. It pushes out in all directions. Secondly, pressure in a fluid, the magnitude is computed by considering what the type of material it is. So water or oil might act differently. So we consider the density, which can be shown by the density or the specific gravity here. But also, it's dependent upon the depth inside the fluid. And that's measured from the surface of the fluid down to the point where you want to consider what the pressure is like. And lastly, pressure always acts perpendicular to any surface. And we're going to show you what the pressure distribution looks like here on the left-hand side here. So, because on the left-hand side of our gate, it's at a shallower depth, it's going to have a lower pressure. And because on the right-hand side, it's at a much deeper depth, it's going to have a higher pressure. And because the magnitude of the pressure is a linear relationship with height, it's going to be a smooth transition all the way down, gradually getting to its maximum value at the bottom of the gate. And it's always going to be acting, of course, perpendicular to the surface. Okay, so how are we going to utilize this information to get to this force we're looking for? So we're going to consider this gate to be in static equilibrium, and we're going to consider all the forces and torques acting up and down this gate from the top all the way down to the bottom. We're going to use a free body diagram for that. One more detail here, this little creepy eyeball is trying to show you that from the perspective of this eyeball, this gate is going to be a 2 by 2 size gate, and the y-axis is the vertical and the x-axis is a horizontal. So how are we going to incorporate this pressure distribution though? This is kind of the new cool thing we need to consider. So this pressure distribution says basically there's an increasing value of force as we go from the top to the bottom, pushing on this plate. And we know we can add up forces to produce a resultant force. And so since the bottom of this pressure distribution is at higher forces, that resultant force is going to be skewed away from the centroid down towards the bottom a certain amount. That's all well and nice, but sometimes this resultant force is kind of difficult to compute, and also the location where it's acting at is kind of difficult to compute. So we'll use an equivalent modeling process here that we described previously, and here's this reminder. So instead of this one resultant force, we're going to model it as a pressure force acting at the centroid and a couple acting at the centroid. And these will just be a lot more easy to work with. First off, the center of an object is always a lot easier to find, and also these values are easier to compute. So let's look at that. So we're going to substitute for this pressure distribution that force from the pressure at the centroid and that couple. Okay, so let's go through and compute this stuff. So let's find that pressure at the center of the gate here. And to do that, we already described how to find the pressure in a fluid. We're going to multiply that times the total area, but this pressure is going to be acting at the center. Okay, so that's going to be right here, right in the middle. Okay, and to do that, specific gravity is fine, the area is fine to calculate, but let's look at this just carefully for a second. So that's the depth to this point in the surface. So we really got to go down 1 meter, and then halfway of this vertical distance from end to end of this guy that we already know is root 3. So it's going to be 1 plus half of root 3 to right about here. And hopefully you can appreciate where I came up with these values. And when we do all that, we get 73.15 kilonewtons. Next, let's talk about that pressure couple. So we previously, in our other lecture, defined this, but so it's going to use specific gravity, and then the second moment of inertia, which basically describes the rotational property of this rectangular surface around like this in a counterclockwise direction, and cosine beta. Let's look at the details. So a second moment of inertia is a pretty common thing for a rectangular surface like this, and you can go look it up easily enough. It's 1/12 base times height cubed. And so we put that in. And then we start putting our values here, and we put in our second moment of inertia stuff. Now, this cosine beta thing is, I want to slow down for just a second for him. We know cosine is just a ratio of sides of a right triangle. So if we look up here, we can kind of see this right triangle. Here's our beta, angle beta. It's defined as being between the surface and the vertical line, okay? And so if we trace out the little right triangle right here, like so, okay, you can see that instead of going cosine of an angle, we can just put in adjacent over hypotenuse. And hypotenuse is going to be 2, and the vertical leg is going to be root 3. See? Hopefully you can kind of see how I came up with this ratio I substituted in here. And when we plug in all those values and run the numbers, we get 11.32 kilonewton meters. So we're totally ready to try to find our goal here, the force at B. Okay, so to do this, we're going to focus on taking the torques about the hinge up here at point A. And so it's in static equilibrium here, so all the torques should cancel out. So we're going to go from top to bottom, consider everything, and then solve out for B. So when we do this, we first start with being in equilibrium, and then we start at the top. And at the top here we have two forces, but they're actually acting on our point of rotation we're considering, so they don't have any moment arm, they'd produce 0 torque. So we have our 0 here. Next we go over to weight, and we get that it's weight times 1/2. How did we get that? Well, we know for torques, the perpendicular distance is what we really are focusing on. Since weight acts straight down, if we can just find this perpendicular distance from A over to the line of action of our weight vector, we got it. And since up here we know from this side to this side, horizontally is 1 meter, our weight is acting at the centroid, this is actually going to be half of 1 meter over, and that's how we get our 1/2. Next, we talk about this pressure force here. It's acting at the centroid also, but it's defined as acting perpendicular to the surface, business pressure. Okay, so it's the perpendicular distance that's important. Since this whole gate is too long, this must be 1 over from here to here. Okay, next, we have our pressure couple, and then we have our normal force, which we know is going to be acting perpendicular to the surface of contact over here, and so it's horizontal. And since we're adding up torques, we know it's the perpendicular distance from our axis of rotation to our line of action of our force. And so we know that from here to that line of action of our force is root 3. Hopefully you can appreciate how I got this. So we know we found the couple, we found the pressure force, we know the weight. We only have this force B that we need to solve for, and we get 45.88.